out to be useful for somebody. Okay, so first, before we start, are there any questions from anybody? Okay. So our goals today are to mainly finish talking about Python functions and then start talking about Python classes. Some reminders, by the way, you should turn in your homework, meaning send an email to that address by Wednesday before class, because I'll check and see whose names are listed there in the email. Also, I have office hours tomorrow at noon, as usual. And I guess that's it for reminders. And also, if you're interested about what's coming up, after finishing off Python, which we'll get pretty far with today, the next thing we're going to do is talk about Python. So we'll talk about compiled Python. So today it's finishing off Python functions and then defining Python classes. And then right after that, we'll talk about try except finally, which we won't do today, so exception handling. And then after that, we'll talk about modules and how to package up your code for distribution. So that will certainly get done by the end of this week. And then we'll be on to Python and then other things. Okay, so variable number of arguments. So we talked before about how to define a function. You say def, then you give the name of the function, and then open parentheses, and then you give the variables, which will be the input to the function, and then possibly some of them have default values, close parentheses, colon, and then the entire body of the function is indented. But what if you want to make a function where the number of arguments isn't pre-specified? So for example, you could call the function with f of, and you could just give any number of arguments. How do you do that? Or, what?
Pass in a list.
You could pass in a list, but what if you want them to be literally separate arguments? Because, you know, who wants to have to write extra brackets there? So, but you could certainly simulate everything I'm doing. Like, you don't need these additional features necessarily, but because you could simulate everything with just a list or something like that. But it's very nice that you can pass in additional arguments, or arbitrary number of arguments. Also, here's another thing. Suppose you have a list with some unknown number of entries, and you want to call a function and give some of those entries or all of them as the inputs to the function. And the function takes its inputs as separate values, as separate entries. Then you have to do something beyond what I've showed you so far. So here's how it works. There's a pretty straightforward, nice way in which this works in Python. Ooh, crap. You can see that there should be some stars there that are missing because my markup language here is, I'm using Markdown, and it's, the stars are interpreted as emphasis. So that's not good. Let me just fix that. In Markdown, star means emphasize, but it's kind of bad if star is what you're using in the code. Oops. Okay, so there. So here's what you do. All you have to do is define your function, and then there's some special things you can put instead of positional arguments or arguments with default values. You put star args, and what will happen, and args can be anything, it doesn't have to be called args, it can be star and then any valid identifier. And what will happen is that in the body of your function, args will be a tuple with values equal to all the positional arguments beyond the ones that were already given here. So there you are. It's a way to give an arbitrary number of positional arguments. Similarly, star keywords, and I call it KWDS here, which is traditional, but you could call this any valid identifier. When you call your function, and when the code runs, inside the body of the function, keywords will be a dictionary. And it's a dictionary with keys, the named parameters that the user specified. So if the user said, call a function f with foo equal to something, then those will be given right here. Okay, so it's as simple as that. Basically, you do some extra notation when defining your function, and when you do that, just making this bigger so you can see, you do some extra notation when defining your function, and then right in the body of your function you'll have a tuple available, which has all the extra positional arguments, and a dictionary available that has all the extra named arguments. Okay, so it's pretty straightforward, and I'll show you some examples. Moreover, in the other direction, if there's a function and you want to call it with a whole bunch of separate arguments, and they're in a tuple, you just put a star in front of that tuple and call it, and what it'll do is it'll be exactly the same as if you took each of the entries out of the tuple and were to put them into the function with a comma between them. Likewise, if you have a dictionary, you put 2 stars in front of it, and then it will be exactly the same as if you call the function with key equal to value for each of the entries in the dictionary. With the caveat that function, the input parameters to a function are always strings, so that their names are strings. So if this dictionary right here, if the keys are not strings, which you can have in Python a dictionary, the only requirement is that the keys are hashable, that they're immutable. They don't have to be strings like in certain other languages. So they'll get, so funny things might happen in that case. But as long as you avoid that situation, you're okay. Okay, so I'll just show you some examples. So here's the first example. Let's define a function f. It takes 2 positional arguments and then an arbitrary number of additional positional arguments. And then after that, an arbitrary number of keyword arguments. And then when you call the function, what will happen is it'll print out all the stuff that got defined specifically for that function. So locals is a dictionary, and it will be equal to, it'll give every single thing that got defined, especially for the function. So now let's call it with 2, 3, 5. 5 is an extra positional argument, and then 1 keyword argument, ABC equals 12. So x gets set equal to 2, y gets set equal to 3, args is a tuple, which is the tuple of length 1 with 5 in it, so there was 1 entry which is 5, and then the keywords thing gets set equal to the dictionary with key ABC and value 12. So basically this one example, just what's up here, kind of explains everything, hopefully. So there you are. There's one funny thing here that you might notice. Does anything look a little funny to you? Yes? Exactly. Yeah, that's the funny thing. And you're absolutely right. That is the funny thing in this picture. So in Python, and since this could easily cause trouble, I'm going to write it on the board large. Let's say, so in Python, remember a list you give square brackets. So here's a list with 1 entry, which is 5. Makes perfect sense. Here is what you might naively think would be the way to write a tuple of things with 1 entry named 5. Because in Python, the way you give a tuple is with parentheses. And this would be a perfectly valid way to give the tuple 1, 2 with parentheses. However, here, this is also the expression 5, because parentheses, you can just put those around an expression. So it's ambiguous. And, I mean, also in mathematics, really, if somebody wrote parentheses 5, you don't really know if they're talking about like a 1 tuple or a vector or something, or just an expression that happens to have parentheses around it. So that's the problem. And in the Python language, what the Python people did was they said that if you want to give a 1 tuple, you have to put a comma after it. And it'll also print that way to remind you that this is not an expression, it's a 1 tuple. So this is how you give a 1 tuple in Python. So you'll see this if you're reading through other people's Python code, or you find yourself trying to write a 1 tuple down. And if you don't remember what I'm telling you at this very moment, you'll probably try to type something like this when you're trying to give a 1 tuple, and it just won't work, because this is exactly the same thing as 5. This is equal to Python 5. because you just put parentheses around the expression. Whereas this is a completely different object. It's a tuple that happens to have 5 in it. Okay? And this is less annoying, though it is annoying, less annoying than the other idea for a solution to this, which you can use, which is you can explicitly write out tuple and then give the list 1 entry 5. So these two are equal. This is another way to make a 1 tuple that has the entry 5. Okay, any questions about this? So please remember this, because if you don't, then you'll get frustrated for an hour while you figure it out. And what do you think you would do to make a 0 tuple? So a tuple with no entries in it. With a list, it would just be open bracket, open square bracket, close square bracket. Okay, let's see if that works. Syntax error. Okay, so that does not work. Okay, let's try that. What are the odds that's going to work? Pretty high, because it's so annoying to have to write all that out. That works. So the way to make a tuple with nothing in it, make 0, is to do, the only way to do it is to do a tuple. You can't just, it would be natural to have it like this, but that doesn't work. So, yes?
So, brackets inside tuple, when you leave those out, it helps us see.
That might work too, actually. I don't know, actually. I just don't know. Never tried that. That might have worked. There's no indicator.
What about if we send it on?
Let me just see if the... Okay, so that also works. Good idea. So you can also make a 0 tuple like this. And then you're asking about none. I kind of hope that doesn't work. You have none here. I don't know. That doesn't work. So what tuple does, this function, I guess when it gets an argument, it tries to iterate over the things in the argument and make a tuple out of the result. And none can't be iterated over. That is a choice. Maybe you could have defined things where none could be iterated over. Remember, this iterator thing, we're about to see how to define classes. With classes, you can just define double underscore iter double underscore, and if you define that method, then that class can be iterated over, or instances of that class can be iterated over. But for none, they decided not to make it possible to iterate over it, and hence tuple of none doesn't work, which is an error. Okay, any other questions? Sorry that the line numbers are off for this entire worksheet that I wrote over the weekend, so I haven't got around to line numbers. All right, now let's look at a few more similar examples. Okay, so here's an example. Okay, here's another example where we call the function just give multiple keyword arguments, and notice our dictionary now has multiple entries in it. Here's an example in the other direction where you call a function and all the inputs are specified this way. So what I've written there is completely equivalent to doing f of 1, 2 stuff equals 1, 2, 3. These are the same. So we should see the same output twice. Okay, and notice that you do. All right, and that's it. So the takeaway to this is you can easily define functions in Python that take an arbitrary and unprespecified number of positional arguments or keyword arguments. Moreover, you can call functions that take positional or keyword arguments and give as input a tuple which will unpack into the positional arguments, or a dictionary which will unpack into the keyword arguments. Good. It's a pretty clean, simple solution to a standard problem that you have in most programming languages. I'm going to show you a bunch of some Sage-specific things that are just kind of within the context of this whole idea of keywords. The keywords are strings. So when you call a function with, say, f of foo equals 5, that foo, even if you happen to have defined something called foo elsewhere, some really complicated and interesting Python object called foo, when you call the function with a positional argument foo equals 5, it knows nothing about whatever other foo you might have defined. It's purely thinking of it as a string, which is a little bit confusing given that it doesn't have quotes around it. And in Python, most of the time when you type something without quotes around it, it's not interpreted as a string. So let me show you some examples where this can cause surprising subtlety in the context of algebra, which will serve a dual purpose of actually showing you some interesting Sage code. And I'll tell you a little bit about what's going on behind the scenes that's beyond what you'd find in Python. So untangling this a little bit, here what, I'll make an extra line that says a little more here, GF7. So what GF7 does, I'm sorry for the jump that happens every time I evaluate. What GF7 is the finite field of order 7. So that's implemented in Sage, and the code to make it's called GF. Sage has a highly optimized implementation of finite fields that comes from a C++ library called Jabaro. And I think this is extremely fast as long as the cardinality of the field is at most 2 to the 16. So this is something that's highly integrated into Sage. At the same time, if you ever need to work with finite fields in some other project that can use C++ libraries, this is an excellent library to use, written by a French computational number theorist. So GF7 and indeed GF, like you can make other finite fields like this if you want, say of non-prime order. Whoops, that one's going to be kind of boring because I didn't print it out. So this is a finite field of size 7 cubed. So that's how you make them. What this notation means in Sage, and it's modeled on similar notation in Magma, this dot angle brackets notation. This is not valid Python notation. A dot angle brackets A equals and some constructor over here. So what this means, so first this isn't valid Python because in Python, if you give an object dot and then something after it, the something after the dot has to be a valid identifier, which is a sequence of letters and numbers and possible underscores, and it has to start with a letter. And this simply isn't such a thing because it starts with a left angle bracket. So when the Sage preparser encounters this, it knows that it should be interpreted differently. If you were to try to type exactly this into pure Python, you'll immediately get a syntax error. And what this means is create the object k if there's some sort of part of the object that needs a name. So in mathematics, often you consider a polynomial ring in some variable or variables or some sort of structure, and those variables have specific letters that you name them. So it's something that comes up very commonly in mathematics. So here, in that particular example, this A refers to an element of the finite field that generates the finite field as a field over GF7. So if you were to compute, for example, its minimal polynomial, it would be irreducible of degree 3 over GF7. So what happens when you evaluate this in Sage, it unwinds it a little bit. You can see what it, in fact, turns it into by typing preparse. This is something you can do at any code at all, ever, in Sage. If you say preparse, and then give some string as input like that, it will tell you what it turns it into. So in this case, k.a angle brackets a, whatever. If you're using something that doesn't make sense in Python and you wonder how is Sage interpreting this, just type preparse around it. But here it says it makes k be this finite field where it names the generator of the finite field a, and then it assigns to a that generator. That's what this second part of the line does. So now after that line is evaluated, the variable a will be defined in your global scope, or your whatever scope you're working in, and you can then use it. So another example of that is right here. What this does is it defines the polynomial ring over the finite field of order 7 in two variables called x and y. And then right after you evaluate this line, x and y are ready to use. Actually, so this, I raised it to the power of 5, which is kind of boring, but if I raise to the power of 7, because we're working in characteristic 7, you see that instead of getting a whole bunch of intermediate coefficients, they're all divisible by 7, so reducing everything mod 7, you end up with just x to the 7 plus 1 to the 7. So this is just an example of doing arithmetic, but where the numbers, all the numbers involved are always reduced modulo 7. You divide by 7 and take the remainder. And also in Sage, if you have an object and you say show the object, it'll exit it. But the subtlety relating back to function calls and keyword arguments is that if you write f of x equals 3, y equals 5, which is a pretty natural notation for calling or for doing a substitution, and what this does is it substitutes 3 in for x and 5 in for y, then it doesn't actually know anything about the variables x and y that are defined here. It turns them into strings and then uses those to identify them, which works perfectly fine. But it's worth knowing about that because you can deviously define the same polynomial ring, but you can name both of the variables x if you want. They're still separate, but you can name them both x. And then calling in this way won't work. So here's an example of that. So start over, but now you want to be really devious, and you name both of the generators of your polynomial ring x. So what that means is you have this polynomial ring in two variables, but you happen to have said, hey, why don't you print them both as x, even though they're completely separate variables. Kind of a weird thing to do, but it's supported. There's a notation in Sage which is exactly like it is in Magma again. If you do R for any object at all that has generators, and in mathematics, lots and lots of objects have a canonical set of generators, or they're equipped with extra structure that gives them a set of generators. For example, if you have a vector space that's got by taking the span of some linearly independent vectors, then those vectors would be kind of the extra structure of generators. Or if you just have some random vector space, maybe the vectors in a reduced row echelon form basis for that vector space would be generators. Polynomial rings, the generators, the indeterminate variables are the generators. So in mathematics all over the place, especially in algebra, you have lots and lots of structures that have generators. And one quick way of accessing them, which is not valid Python notation because these numbers aren't valid Python identifiers, is to say r dot and then give a number, and it gives you the ith generator starting at 0. This just gets converted as follows. Let me show you what this gets pre-parsed into. I better evaluate that. Whoops. Else strip. Pre-parse. Oh, I have to give. I was trying to pre-parse the variable rather than the string that would get evaluated. So what it does is it simply turns r.0 into r.gen0. So it's just a little tiny shortcut, but it's actually really helpful in practice. And then adding together the first variable of our polynomial ring plus 2 times the second variable of our polynomial ring results in x plus 2x. But these x's are completely different. They just happen to print in the same way. So you have to watch out for this. And the subtlety is, what if I do f of x equal to 3? Well, which x is it going to use? There's some rule, but it's kind of arbitrary, but you have to watch out. If you want to be very precise about how substitution works, instead of using this function call notation, it's better to do f.subs, which allows you to specify what the variables are, and you get to use an actual dictionary. The point of all that was just that when you use keyword arguments to a function, unless the keywords really are strings, there's a lot of things that you would naturally maybe spend a lot of time thinking this is the way to write but they turn out to be somewhat misleading and can lead to all kinds of subtle bugs if you're not careful. And instead, maybe you just want to make a function that takes a dictionary as input. So sometimes a more straightforward data structure is a better idea. Okay. All right, the next thing is docstrings. So when you define a function, you're allowed to, or you're encouraged, in fact, to give a string immediately after the definition of the function. This is called a docstring in Python. It's documentation for that function. And it's completely optional. You don't have to give it. But if you just give a string right after a function is defined, then that string will be attached to the function. You can get it at runtime. There are lots of tools that, like documentation tools for Python that will extract those strings and make, for example, the Sage reference manual out of them. So the Sage reference manual is mostly constructed out of these strings attached to functions in Sage. There's a lot of thought and controversy and arguments that goes into when you're involved in a big project, what should be the format of this documentation string. So for example, is it okay if it has more than 80 characters in a row? So people will get really annoyed if it has more than 80 characters in a row. The punch cards are really stupid sometimes. How should you format it? And there's, I think, 3 different Python enhancement proposals, one of which was canceled. And they're about the format of docstrings in the implementation of Python itself. Python, if you download the tarball and look at the source code, it's this C program that builds from source in about a minute. And then in addition to that, it's a very large Python library, which has a lot of functions in it, many of which have docstrings. And there's a convention on how those should be formatted. In Sage, we have probably 40 or 50,000 functions at least, maybe a lot more. And as of now, I think well over 90% of those functions have docstrings with examples in them. So commonly, the way we do it in Sage is we write things like example, colon, and then we put explicitly examples in that illustrate the function. And I wrote a tool called coverage that goes through the Sage library and checks to see if there are actually examples that illustrate functions. And I think solidly over 90% now have examples of all functions in Sage. Yes?
What's a little argue?
That's an important question. So when you define a string, you might be tempted to put some LaTeX in it, some backslashes. And backslashes will be interpreted as word escape things. So for example, you put a \n, you'll get a new line in a string in Python. If you put an R before defining a string, then it will interpret the backslashes as backslashes. It's a raw string. So there's no funny formatting that goes on. So that's the reason for the backslash, or for the R. So it'll be very common in doc strings to put an R in front. The various tools in Sage have support for LaTeX all over the place. So for example, when you're using the Sage notebook and you look at a doc string, it will typeset it nicely. The automatically generated documentation for Sage, like the reference manual, it typesets all of the mathematics. It's a math library, so there's a ton of support for math, and LaTeX is, I know many people here probably have never heard of LaTeX, but this is an example of LaTeX markup that describes this. Sum AI equals a squared plus b squared plus c squared. So, the thing with LaTeX though is it's very backslash heavy, like lots of different things like sine, cosine, sum. Basically any function when you use it in LaTeX markup has a backslash in front of it. So if you don't put an R in front of your string, what will happen is your string will silently appear to work, but then when somebody looks at it, it'll have some like weird mangled characters in the middle. Okay, so it's a good habit to get into. And it's very rare that you'd really want to put a \n or some escape character in a doc string because it's a multi-line string, so you can just put current things. That's also what the triple quotes mean. In Python, you can delimit a string with either double quotes or single quotes, depending on your mood. The only thing is that you have to be consistent. If you're going to use a lot of single quotes inside of your string, then you might want to delimit it with double quotes so that you don't have to escape the single quotes. So for example, inside of this, because I used an R, I could certainly use single quotes or double quotes, no problem. But let me just show you some examples of strings. I mean, it's just another sort of Python topic, but if you use a single quote, or sorry, a single double quote, then you can do stuff like that. And you can just freely use single quotes everywhere inside of it. If you were to use a double quote inside of here, that would be a problem because that would mean the string ended. So that would be bad. On the other hand, when you type a double quote, you have to hit the shift key, and your finger might be tired. So you might want to use single quotes because it's less work. And then you can also use double quotes inside with no trouble at all. So like that. And you can always do something like this, like you do a quote like that, and you could do backslash quote. Boom. That's fine. That allows you to put a double quote inside of a double quoted string. And you can do the following. If you put an R there, then you can, what can you do? Actually, then you're in trouble. There's no way to put a double quote inside of there because you can't escape, and you put an R there, so you're not allowed to, or backslashes will just mean backslash. So at this point, you can't do it. There's also string formatting in Python where you can kind of make little templates for your string and then fill them in, and so on and so on. Oh, the other thing about, so triple quoted strings, you can use either 3 triple quotes or 3 single quotes in a row. They're nice because you're allowed to span multiple lines. Whereas with a single quote string, you're not allowed to go on another line. The entire string has to be on one line. Whereas it sounds pretty crazy when you think about languages that don't have white space sensitivity, but in Python with white space sensitivity, single quoted strings can't span multiple lines unless you can use a backslash at the end of a line, but other than that, you can't do it. Huh. Okay. In any case, here's a function, here's a docstring. It's optional, but a good idea to include docstrings in your functions, especially if you, I mean, it's better than just putting like a comment. A comment in Python is just a hash. So this is a comment. Docstrings are better than comments because comments just completely disappear at runtime, whereas the docstrings are there. Somebody can be running your code and they can look at the docstrings and get additional helpful information. They can't look at the comments. So that's why you may want to use docstrings. In Magma, they have something that's just like docstrings, except they're not optional. You have to give them. So you see a lot of empty ones when you're storing code. So let me evaluate the above cell, which should print out some funny strings. But the cool thing is now I can type this, and you see that at runtime, I can access the underlying docstring. And there are tools to make this really nice. If I were using the Sage notebook or the other notebook I was using last week, then you could put a question mark after this and hit tab, and you get some nice thing that pops up with syntax highlighting that shows you the documentation for the function. Or in, say, IPython, you could type F question mark with the return key and you'll see the documentation. So this is known as introspection, where you're finding out at runtime about properties of your system. You're introspecting it. So I strongly encourage you to write docstrings. And for Sage, there's a whole section of the Sage Developers Guide, which is a document on the Sage website, which is all about the exact format of docstrings that we want to have. When you try to submit code to Sage, if it doesn't have the property that every single function has a docstring with the appropriate format, and every single function has an example illustrating its usage that works, then the code will be rejected until that's fixed. And we've had that policy for the last 5 years, I think. And I think few people have refused to submit code because of it, though it has happened. And then one person at Georgia was able to somehow cleverly sneak his code in even without getting all coverage done, which really annoyed me. So I pressured him hugely and he eventually got the coverage up to 100%. That's the quadratic forms code. Okay, so there's doc strings. And oh, I should emphasize that with Sage, we have lots of examples like this that you'll see all the time. Whenever you, basically anytime you look at the documentation for a function, you'll see examples because they're, well, at least the probability 90% you'll see examples. They work. That's the neat thing about the examples. So we automatically test them on a wide range of platforms using a build bot. They work unless, they might not work if, like when you look in the margin, so we have an annotation system that I came up with where you can do, for example, optional, and then this isn't run, this test won't always be run. It's only run if the system's being tested with a certain flag that is very rarely used. And it'll be things like requires Mathematica, something like that. So there are a couple of tests that are difficult to test because the environment requires some like commercial software or something funny. And those are likely to work, but maybe not so, they haven't been tested necessarily. Whereas the stuff where there's no annotation has been tested. And there used to be, I think I mentioned this already, there used to be a lot of them where it would say hash random. And what that meant was that the input was evaluated, but we did not check that the output was as claimed. And what we did was Carl Whitty wrote a random seeding function, or a system that would seed all of the random number generators in the same way, and then ran it before each doc test. And then we were able to have examples that are random, but at least the random seed was always the same, so you could see the same output every time. So that was kind of nice. Okay, moving on. So I think that it's just another example of introspection, but that'll pretty much finish talking about functions. This is an example of something called the inspect module in Python. It's a module that will tell you about classes, functions, variables, whatever in Python. So if you do inspect.getArgSpec on a function, it will tell you what the arguments to the function are. Basically, it'll tell you kind of what you would see if you were to look at the source code, but it's all done at runtime, which is nice. And there's a Sage version of this inspect module called Sage_inspect that has lots of tricky enhancements to it that we found we needed, especially for supporting Python code. Okay, moving on. Classes. So, unlike some languages that have classes bolted on in funny ways, like Perl, in Python, classes are really object-oriented programming is really part of the language from the beginning. So it at least offers full support for object-oriented programming. Mainly that means you have multiple inheritance. So you can have a whole bunch of base classes for a class, and you can do operator overloading, for example. So you can say, you can redefine what A plus B means, which is, these are very important features in mathematics. Operator overloading is really, really nice because you want to be able to define a class of objects and then do arithmetic with them using natural expressions. Like you want to be able to write A plus B instead of always having to write MPZ underscore add A comma, or C comma A comma B. This is what you have to write when you're using the GMP or MPIR libraries. So it's nice to be able to do this sort of thing. C++ is a kind of a pioneering language in that it had extremely extensive support for all this sort of thing, and it was also popular, or is also popular, but there's of course many predecessors to it. Okay, so I'm just going to show you how it works. See, this looks a little messy, so let me shrink the font slightly so it all fits. This is just kind of over. Okay, so all right. So here is an example, a working example of a class definition. What this will do after we run it is make it so that there's, in a sense, a new data type, kind of like list or tuple or int or whatever else, but it's going to be called math list. This is going to be an object that's kind of like, well, it's it's exactly like a list in Python, except what's here. So we'll change some aspects of how lists work. So here's the notation for making a class in Python. You say class, then the name of the class, and then optionally, in parentheses, you give a list of other classes or types. And they're separated by commas. It's not a list literally, it's just you give a couple of other optionally class names, not as a list with a square bracket. Using this one literally is list, which is a data type that's built in. Sorry about that. Totally optional. There's also something you can derive from called object, which is just some kind of generic base class that impacts the method resolution order and some of the other subtle properties of a class. Okay, so you say class, name of the class, something in parentheses, colon. Note that this is almost exactly the same as what you type when you're making a function. When you define a function, you say def, name of the function, open parentheses, some stuff, close parentheses, colon, and then the entire definition of the function, everything else goes indented in the body. The same is true of a class. You indent, preferably 4 spaces, and then you put all the code that defines how the class behaves here. And what will happen is, what this does is it makes a class that's exactly like a list, except that when you create it, it'll call this function, which in fact just calls the list creation function. But you can put some special code in here if you want it. It prints differently. So lists normally print with square brackets, but our list, when you print it out, it's going to print with angle brackets. Also, I'm overloading the add method. You can't really tell, but those are 2 underscores. And since this is super important, I will write it over here. Underscore, underscore, add, underscore, underscore. 2 underscores. There's a large number of functions in Python that look like this, like double underscore sub, double underscore mul, double underscore armul, double underscore neg, etc. This is how you do operator overloading. What you do is you overload, you redefine in some derived class, or in your class, these functions, and then you'll be able to do it. So, for example, for lists as built into Python, when you use plus, you do v plus w, it concatenates the 2 lists together. Which you should feel somewhat abhorred by as a mathematician, because you should never write plus for a non-commutative operation. And concatenating lists is non-commutative. So you could be annoyed by that, but in any case, that's what they do in Python. Some people would say it should be an asterisk. But kind of like, multiplying 2 elements of a free group or something. In any case, our list will have the our math list will have the property that when we do add, it's going to be component-wise, kind of like a vector. But if we wanted, we could also define mul for 2 of these things. Mul will be what happens when you use the asterisks, and that will concatenate them. Hopefully. Okay, so there's dozens and dozens of these special methods. You can look in various reference manuals and so on to see what they are. Yes?
Are the special methods there for everything, or does it depend on what you put as your, like that you put stuff there as your class?
They're there for absolutely everything.
Yeah.
However, if I didn't put any class here at all, or some other class, then none of them, then maybe very few of those would be defined. But you can define them for anything. So you can make absolutely any Python class you want. You can define an add method, for example, and then plus will work. So they don't have. So if you just start with a blank class that doesn't derive from something else, then it's not going to have those methods. You'll have no methods at all. Except there are a few special methods that you have. For example, there's a double underscore. They're called dunder methods. There's dunder dict, D-I-C-T. That gives you, if you call it, or if you, actually, It's just an attribute, but you automatically have it on a class, and it has keys, the names of all the functions or methods, and extra data you have attached to your object, and then values are the actual functions or data. So really kind of secretly behind the scenes, a class is like a template for making dictionaries that that kind of have certain syntax for how to use them.
How do you make class fields?
Class fields?
Yeah. Well, like, if you're like,
From a what?
from a Java perspective,
Whoa, wait.
like
Now I'm really confused.
so like,
I don't know what a class field is, except I do know what a class field is in number theory. And
just like a some chapter.
oh, okay. Yes, sorry. Oh, the field of a class.
Yeah.
Yeah. Yeah, because in Sage there's a lot of support, or there's a lot of subtle support for objects called class fields, which are kind of like basically maximal abelian Galois extensions of certain number fields with ramification properties, which are called class fields. And no. Actually, the question makes sense now that you say it. It's pretty. You just do. So there's this parameter self, which is the first parameter to absolutely all these methods. It's just like this in a C++ and probably the other languages. And the only thing though is you have to explicitly give it as the first input, as the first argument, and you can call it anything you want. It's just the tradition in Python to call it self. If I wanted to call this, I don't know, this, I could. Just that people don't. In any case, all you do is you just, so to make my class field, I can do, I don't know, what's your name? Taylor. Okay. So this class, each instance of this class, when created, will have a field called class underscore field with value Taylor. Okay? You can also have a single field like that that's spans across all the classes. And to do that, you would move the scope out, and you would just write something like this. Oops, 0. Okay, but I'm not going to do that. All right, so let's evaluate this code, see if it still works. It does. Okay, now let's make one of these things. And there it is. Let me do v.classField so you can see that it has that. There it is. So you can access that attribute, as it's called, by just doing v.NSName. Okay? And so that's how you store extra data with instances of the class. And you could change this if you want by doing if I change that and then print it, it will of course changed. And now it's equal to like nope. It can be absolutely anything. It's just like a dictionary. It's really like just setting a value for a given key in a dictionary. Yes?
If you want to make those private, so you can only change it with a function class
Yes.
field changer,
There's something called properties, where you have a getter and a setter, and the notation's pretty clean in Python. Unfortunately, it was introduced before I wrote a lot of code, and so I don't remember it off the top of my head, because I never use it. But they're called Python properties. They completely solve that problem, though. Properties solve the getter setter. Basically, you associate a function for getting it and for setting it. And then you get to use exactly this notation, but it'll do type checking and so on. And when you access it, it'll call a function. Very nice. Okay, so we'll start again with further discussion of classes on Wednesday.
So, Code Academy, how many blocks of exercise am I supposed to do? Like I did 3.
As many as you feel that you can.